So in this lecture we'll talk about conservation of momentum. In the last lecture we defined momentum as this, and because v is a vector, v is the velocity vector, so p should also be a vector, and because m is just a scalar, and this we derived this from the definition F equals ma. Now we have been writing like this for we did that many times, but actually by this we mean by sum of all the forces, which means they are with sum all the forces available, and that this with the vector sum of all the forces equals mass times the vector sum of the final acceleration. So that was we meant all the time. But let's talk about conservation of momentum. Now we also said in the last class that this can be written as F equals m dv over dt, which was also written as dp over dt, right? Just using these definitions. And this is nothing but Newton's second law, which says the rate of change of momentum is nothing but equal to the force applied. Okay, let's take a special case. Let's take a case when sum of all the forces is 0, which means there is no force acting from outside on the particle or on the system. If that is true, then we can say 0 equals dp over dt, that is rate of change of momenta is 0. So if rate of change of momenta is 0, which means what? It's not changing with time, and that means p initial equals p final, which means for any time t initial, if momenta is p initial, for any time t final for which momenta is final, they are the same values. There is no change in momenta if there is no external force acting. So if this is true, momentum remains conserved. For example, let's say there is a box and you put in two balls in there which collide with the boundaries and can also collide with among themselves, and let's say they do not lose energy on these collisions. They are perfectly elastic. There is no loss in energy. Okay, so let's say we started with a situation like this, that the first one was thrown like this, the other one was thrown like that, and let's say the momentum of this guy was p1 and this guy was p2. This is the x-axis. Then we actually start with the momentum p1 minus p2 in the x direction, and if you leave it like that, we will observe that after some time the system, we don't know how it will be, maybe it will just keep colliding like this, will still be p1 minus p2 x hat. Why? Because there is no external force acting on the system that is going to change the momentum of the system. There are forces involved, like when the two balls collide, they exert force on each other. When these collide with the boundaries of the box, then they exert force, but there is no external force. So what is important to understand is that this force is actually the external force, a force which is going to come from the outside. So that is the external force. Or you can have a different situation. You can have three balls going like this, and let's say this is p1, this is p2, and this is p3. Then p1 plus p2 plus p3 is the net momentum of the system, because we always talk about system. Here we were talking about a particle, but that can also be extended to a case when we have more than one particle, like we have three particles here, and this should remain a constant. Why? Because collectively the rate of change of this momenta, which is the sum total of momenta, is not changing because there is no external force. Okay, so that is called conservation of momentum, that momentum remains conserved of a system. That is an important word, of a system. The system can be 2 balls, 3 balls, 4 balls, anything else. and it remains conserved if there is no external force. And we'll talk about some examples in the next lecture.